Just as we are exploring space, we once had to delve into the depths of the oceans. Autonomous underwater vehicles, or AUVs, are arguably one of the most important inventions of their time, marking a significant leap in automated exploration systems. They laid the foundation for what we now recognize as unmanned space travel. The basic purpose of any autonomous underwater vehicle is simply to explore the ocean depths, collect scientific data, and perform specific tasks in underwater environments. Given the immense pressure underwater, it's clearly dangerous to send humans. This is where the concept of AUVs come in. These vehicles are critical to ocean exploration, allowing scientists and explorers to reach areas that are inaccessible or dangerous for humans. They're also used to improve our understanding of the ocean, monitor the marine environment, and develop applications in fields ranging from scientific research to defense to the oil and gas industry. But we need to go back to the 1950s, a post-war era hungry for new discoveries. This is where research began, where a host of serious and dangerous problems needed to be solved, problems that could set research back months. So, at the Applied Physics Laboratory at the University of Washington, under the leadership of scientists Stan Murphy and Bob Francois, with the assistance of Terry Ewert, the effort to tackle these challenges began. They started with the most difficult, deep water pressure. They had to use robust designs and highly resistant materials to withstand the extreme conditions of the ocean. But the biggest challenge lay elsewhere: communication. Underwater communication was severely limited by the sluggishness and limitation of signals. This is a problem we still struggle with today, but back then, they relied on an archaic system of tethered cables to relay information, limiting exploration. Navigating complex environments with obstacles and topographic variations requires advanced navigation systems and collision avoidance algorithms to ensure safe and efficient operations. It wasn't until much later that these were developed more efficiently. By 1957, however, they had managed to develop nothing less than the self-propelled underwater research vehicle, which was used to study diffusion, acoustic transmission, and submarine wakes. It was a major step forward. 20 years later, in the 1970s, further advances were made at the Massachusetts Institute of Technology, MIT, and one of these vehicles is now on display at MIT's Hart Nautical Gallery. At the same time, AUVs were being developed in the Soviet Union, although these advances didn't become widely known until much later. Then it takes us to the following decades, the 1980s and 1990s. Institutions such as the U.S. Navy and research organizations such as the Woods Hole Oceanographic Institution began to develop and deploy AUVs for various scientific and military missions. Advances in electronics, computing, and component miniaturization have allowed for the creation of more sophisticated and capable AUVs. Today, AUVs are advanced tools that play a critical role in global ocean exploration. The internal design of AUVs is theoretically quite simple, but in practice, they are complex to assemble because they have to take into account a lot of material information, connections, and so on. However, among the necessary things they must have is their hydrodynamic shape, which reduces water resistance and allows them to navigate optimally. The most important components include their propulsion system, consisting of motors and propellers to move them underwater, not to mention navigation and communication tools such as GPS for surface navigation, acoustic positioning systems, and satellite or radio frequency communication links. These vehicles are also equipped with a variety of sensors, such as cameras, sonar, and temperature, salinity, and pressure instruments, to collect data about the marine environment. To power themselves during their missions, they use high-capacity batteries, or alternative energy systems. Some of their most interesting capabilities and functions include underwater mapping, where sonar and other sensors can be used to create more detailed maps of the seafloor. They are also used for environmental monitoring systems to monitor environmental parameters such as temperature, salinity, and water quality, to study climate change and the health of marine ecosystems, and for marine biological research, mainly to study their habitats, including observing species in their natural environment, and for underwater archaeology. The most important submarines ever made and talked about include, for example, the REMUS. The REMUS, or Remote Environmental Monitoring Units, is an AUV developed by the Woods Hole Oceanographic Institution. Used in missions such as search and recovery, mapping, and marine life monitoring, the REMUS has proven to be a versatile and effective tool. Or the AutoSub Long Range, Bodie McBoatface, developed by the National Oceanography Center. The AutoSub Long Range, popularly known as Bodie McBoatface, undertakes long-distance missions to study ocean currents, temperature, and salinity, contributing significantly to the understanding of global climate. There is also the Bluefin 21. The Bluefin 21, manufactured by General Dynamics Mission Systems, is best known for its role in the search for Malaysia Airlines flight MH370. Its search and rescue capabilities have made it very important in emergency operations. Or the Hugin Norway, developed by Kongsberg Maritime. The Hugin is used for seabed mapping, pipeline inspection, and environmental monitoring, making it an important resource for offshore industry and scientific research. There is also the Slocum Glider. Teledyne Marine's Slocum Glider is used for long-term environmental monitoring and data collection in the world's oceans. Its designs allow for extended and autonomous missions, collecting critical data for the study of climate and marine ecosystems. Let's explore the remarkable progress that has been made. Recent technological advances are greatly improving the capabilities of AUVs, especially in terms of improved battery life, which allows for longer missions. Advanced sensor technologies also provide more accurate and detailed data. Artificial intelligence is being integrated into autonomous decision-making, allowing AUVs to adapt and respond to changes in their environment in real time. In addition, navigation systems have improved, making it easier to operate in complex underwater environments with low visibility. The social and environmental impacts of autonomous underwater vehicles, AUVs, are often overshadowed by their environmental benefits, as they enable continuous monitoring of ocean health, the study of the effects of climate change, and the conservation of marine ecosystems. By providing accurate and timely data, they help scientists better understand changes in the marine environment and develop strategies for its protection and sustainable management. That's why these instruments are not only important for the world, but also for the advancement of technology. As individuals, we must support this research because it benefits both the world and technological progress. The exploration and protection of our oceans cannot be considered less important, as they are necessary for the sustainability of the global environment. Participating in conservation programs and encouraging the development of innovative technologies that will ensure that our oceans remain healthy and productive for future generations. You can help by subscribing to the channel and liking it. See you next time!